Clinker Factor, the cement industry podcast.
Welcome to the Clinker Factor, a podcast from WCA, which looks at the cement industry's response to climate change around the world and other topics of interest. I'm Ian Riley, CEO of WCA, and your host on the Clinker Factor. Now, before we get started today, I'd like to remind everyone that we'll have the WCA conference on May 18th to 19th in Nanjing, China. So do check our website for details and how to register. Today, I'm talking to Sam Draper, founder of Seratech Cement. And Seratech has interesting technology, but also a very interesting business model, and one that I think the cement industry may find rather attractive. So we'll get into that in a minute. Sam, welcome. Perhaps we could start by asking you to introduce yourself and explaining how you came to be working in the cement industry.
Hi, Ian. Thank you very much for having me. Yes, so I'm Sam Draper. I'm the CEO and co-founder of Seratech. And I got into the cement industry almost by accident, really. I trained as a structural engineer, but for some reason that just didn't quite vibe with me as a career. And I thought I would try my hand at research. And so I started a PhD at Imperial College London, and it was looking at cement chemistry. And yeah, it was something I really found a weird undying love for.
Excellent. No, this is something you share with many people in the industry. And
yes, I'm not sure it's something you should ever admit to, though.
From your research work, then you have founded Seratech. So tell us a little bit about how that came about and who Seratech are.
Yeah, so I met my co-founder, Barney Shanks, while we were doing our PhDs here at Imperial. So as I say, mine was in the cement chemistry side of things, and his PhD was more in sort of the processing of magnesium silicate minerals. So it was this sort of overlap in our research, really, which led to the birth of Seratech. So sort of our technology at its core is the sequestration of CO2 within magnesium silicates, and this produces two cementitious materials. We get a silica-based SCM, which is sort of fairly chemically similar to fly ash and other materials we've been using for a very long time, and also magnesium carbonate, which is a binder in its own right, and we can use for concrete products like bricks and blocks.
Okay, so the chemistry of this has probably been known for some time. So what is it that you're doing that is special in this respect?
Yeah, so the overall chemistry is a very simple equation, really. You start with magnesium silicates and you add CO2, and you sort of swap that carbonate bit and that silicate bit, so you get magnesium carbonate and silica. People have spoken about it for a very long time. I'm sure everyone will be familiar with sort of the concept of enhanced weathering, where magnesium silicates are ground up very fine and thrown out onto a beach or a field and left to carbonate naturally, removing CO2 from the atmosphere. But the problem with this is very much, where is the economic incentive to do this? Your product is dispersed all over a field if it stays there and isn't blown away. So you're relying on sort of the inherent value of carbon capture to make this viable. Instead, we use sort of a multi-stage chemical process, which allows us to very efficiently break down the magnesium silicates and then store that CO2 within it, generating these product streams, which really add to the value of the product and produce cementitious materials.
So one of the questions that we ask in the cement industry for any kind of CCU technology is how many tons of the CCU material are needed to absorb a ton, or in the case of a cement plant, probably 1 million tons of CO2. So using your technology, for 1 ton of CO2, how many tons of raw material do you have to start with?
So this is something which magnesium silicates are particularly strong at. To sequester a ton of CO2, we need, depending on the sort of the grade and the purity of the material, between about 1.5 and 2 tons of feedstock, which is, potentially 2, 3, 4, 5 times lower than using sort of waste materials with very low sort of carbonatable percentages in them.
Yeah, or perhaps even more. I mean, I think the typical values for waste materials are perhaps 10 or 20 tons per ton of CO2. And is that because of the chemistry itself, or is it because you're getting a more complete exchange of more complete carbonation in the process that you're using?
Yeah, it's purely down to the chemistry. There's sort of very limited ions and elements which you can effectively carbonate through mineralization. Calcium and magnesium are sort of the main ones. So if you use a sort of a high purity magnesium silicate, which we're very fortunate, it exists quite a lot in nature. It's a hugely abundant mineral. You've inherently got that sort of density of CO2 sequestration potential.
Right. And do you have to have a very pure source of magnesium silicate, or are you able to use minerals that have, a proportion of that in there?
No, so we can process anything, really. So if you look at magnesium silicates and olivine, sort of the the main family we use, they're these sort of magnesium iron silicates. They typically have, 10% of the magnesium substituted with iron. And that's something that we're able to deal with in the process very simply. And we use that iron, we actually make it reactive and turn it into the product. So in some ways it's a benefit. The only thing is, because you can't carbonate it in quite the same way you can magnesium, it does decrease your sequestration potential a little bit.
But it doesn't cause you to produce any kind of waste material?
No, not at all. So our process, one of the great things about it is it's completely circular. We use a sort of catalytic approach, if you like. So there are no waste products generated from the process. It's simply just CO2 and magnesium silicates in, and silica and magnesium carbonate out.
Now, in terms of the availability of the raw material, you're currently using a source in Norway, you told me earlier. How much have you investigated the availability of suitable raw materials?
Yes, so Sibelco have the Orheim quarry up in Norway, which is one of the largest producers of olivine at the moment. We've done some quite extensive studies into sort of the global locations and the geology of magnesium silicates, and they're hugely available. The challenge we sort of have at the moment is they're not used for that much industrially, sort of refractory products. So the challenge here is really how do we scale up extraction of these alongside our technology to ensure that we have sufficient supply. And thanks to technologies like enhanced weathering and other carbon mineralization approaches, this is something that the mining companies are definitely already starting to think about. And there are numerous deposits all over the world which would be suitable. Just now we were discussing the sort of the largest known deposit in Oman, and we were doing the maths on that a little while ago. And if you replaced or if you implemented our technology in every cement kiln on the planet, there would be enough magnesium silicates in that one deposit alone to sequester the entire industry's emissions for 27,000 years. So these are hugely abundant minerals. The challenge, as I say, is just how we extract them and use them in the most efficient way.
Right, but there's currently a commercial source that is sufficient at least to start exploitation of this technology.
Yes, yeah. So there's a couple of million tons of capacity immediately available from Orheim, and I'm assured that sort of is also able to be scaled up very, very quickly.
So let's talk a little bit about the path to commercialization. And where are you at the moment in terms of the scale of your development, and how do you see that expanding going forward?
Yeah, so we're sort of at the very end of our lab development phase, if you like. So in the next 2 or 3 weeks, we're looking to open our seed fundraising round, and that will be geared towards building a small pilot facility, essentially, which will produce just sort of 200 to 300 tons of the materials per year. But that will really allow us to demonstrate the process in sort of an industrial embodiment, using proper equipment rather than lab beakers and things like that. And then that will be the first of 2 pilot facilities, the second with a capacity to sequester about 20 to 25,000 tons of CO2 a year, and then that will be sort of wholly representative of what you would implement in a full-scale cement kiln.
Okay.
And then beyond the end of that, we're currently exploring a licensing model. So we would be able to license our technology directly to cement producers or any other CO2 emitter. Actually, we're sort of CO2 agnostic in our approach. And that would allow them to sequester their own emissions and produce our materials, which they could use in their own sort of downstream chains.
Right. So the first pilot plant you're hoping to start work on this year? Or?
Yes. So the design work for it is already underway with various grant fundings, but then sort of the process of building that is a little bit more capital intensive. So that's why we're looking to raise money to achieve that.
And are you looking for industry partners to participate in that, or to provide CO2, or to utilize the products?
Yeah, so there's obviously quite a few different roles for the cement industry and also the various other partners in the cement and concrete value chains. The CO2 source is naturally a very big one. Sort of the more representative CO2 you can get, the better that de-risks things. And then also early utilization of the products. Exactly as you say, we've done a lot of work sort of on the demand side, working with engineers and developers and major contractors to start identifying development projects that will be using these early materials in. But we're always sort of open to new opportunities and have discussions with more people.
So I had a discussion with Hoffman Green Cement last month, and one of the things that Hoffman had done is to work with developers rather than further up the supply chain. So that for a cement company is a little bit unusual. We've tended not to have so much contact with developers. But I see in what you were just saying that you also were thinking, of starting at the developer end. And I just wondered why, what the logic that led you there was.
I think there's just such an interesting, by which I mean complex, interplay between all of the different parties upstream and downstream of the cement manufacture. And it really does require buy-in from all of these to take a new innovation to market. I think in the last couple of years, we've seen sort of a lot more vocal support from the demand side for new technologies and a desire to really get these into their developments, and that sort of surely has to act as a huge driver for the cement industry. I have participated in panel discussions before with people from the major cement players who have said that they don't perceive there to be a demand for low carbon cementitious materials. And I think the more we can demonstrate that by getting the demand side involved, that's really powerful. I fully understand why a cement company wouldn't want to invest 10 million, 100 million building this new facility to produce a cement that nobody would want to purchase. And yeah, it's only by sort of working with everyone and integrating that appropriately that I think we stand the best chance of taking these innovations forwards.
Yeah, and I think you're absolutely right. Traditionally, of course, the cement industry and concrete industry has produced standard products in large quantities, based on large raw material bodies and siting the plants near to the limestone. And if we weren't talking about carbon, then we'd only be a small part of the total costs of a building, and probably the developers and the contractors wouldn't be terribly interested in having long conversations with us. But I think that carbon it just changes the picture altogether. When we look at 35% of building carbon coming from cement and concrete, then the developers and the contractors are extremely interested to engage in conversation with the industry. And if we fail to do that, there are innovators like yourself and Hoffman and others coming along who are very willing to talk to the contractors, and we need to be careful that we don't miss the boat in that respect. So in terms of next steps, so you talk about the pilot plant. Are there other things that you're doing?
The pilot is definitely the main thing. I think we talk a lot about the scale of the cement industry because it's just so relevant. If you can't produce a material at an industrial scale, and I mean when we talk industrial scale, we don't even mean normal industrial scale. We mean millions, if not billions, of tons. It's absolutely mind blowing when you think about the true scale of this industry. And if you can't meet that, it's probably pretty useless. So huge amounts of our effort go into really demonstrating how the process works industrially, because that's the route to achieve impact, which is, it's what we set out to do, and we hope we one day do have a meaningful amount of success in.
Yeah. So now I was just going to ask you about standards, and in a lot of cases, standards are a barrier to innovative new approaches. Do you find that, or is that not something that's a problem in using your product?
Our approach is sort of very carefully designed to fit within existing standards as much as possible. We deliberately didn't look immediately towards sort of new chemistries. I mentioned my co-founder Barney, his PhD was in processing magnesium silicates. That was for MSH cements. So something that we have an understanding of, but we decided to park initially because, producing the materials and using it as an SCM in a conventional Portland cement concrete fits within those standards. Which, as you say, can be a huge barrier to so many technologies. I think standards obviously exist for a reason, and I'm not going to sit here and say we should throw all standards out the window and just do whatever we want, because that will have potentially very serious consequences. But I think we need to be mindful of the need to slowly and responsibly evolve standards to fit new technologies and not just keep them focused on what we've been doing for many years. But regardless, I think that's not going to be a process that's going to happen in the next 6 months. And a key challenge for innovation within this space is really how can you bring a suitable product to market within the constraints that you have, and that's something that we've really tried to do through our SCM.
No, that's that makes good sense. But so for your silicate products, your understanding is that they would fit into the current standards for blended cement.
Yeah, so chemically and physically they meet the requirements for a P-class pozzolan. under EN 197 Part 1, and then that will allow us to use them directly in sort of SEM 2 and SEM 4 cements. And then in the UK, these are all suitable in BS8 500 for use in most concrete classes.
Yeah, good. Well, that certainly simplifies things slightly for you. So when you look to the future, are there any particular barriers that you are concerned about, and that you, any challenges that you see yourselves having to overcome in the next year or two?
I think there are three main barriers to market for all technologies, and two of them we've covered with sort of availability of raw material. We use these magnesium silicates, which are hugely abundant, and then standards, as we've just spoken about. I think the third one is cost. Cement and concrete have done such a roaring trade in the past based on being incredibly versatile, incredibly cheap building materials. And quite simply, that can't change if people are going to continue to use them and build the structures they need to build. Through our process, we essentially generate three sources of value. We're sequestering emissions from a cement kiln, we're producing a complementary cementitious material, and we're producing magnesium carbonate that can be used for, as I say, as a binder in blocks or other construction products. And those three sources of revenue essentially give us very strong economics. So we're optimistic, and all of our sort of techno-economic modelling has shown that we can produce our core products below the price of incumbent materials. So if you look at sort of GGBS now, if you're lucky, you might get it for 90% of the price of Portland cement. If you're unlucky, maybe 120. So we're targeting pricing our RSCM at about 80% of the price of Portland cement, so that there is this economic incentive as well as the sustainable and emissions reduction impacts that you're having through that.
Yeah, no, thank you for that summary. And I think that's really encapsulates why Seratech's got a very interesting technology. I wish you well in developing it, Sam.
That's great. Thank you very much, Ian.
Thank you. So thank you for talking to me today. And just to close, I remind everybody again of the conference, and do go to our website for further details. Thanks for listening to the Clinker Factor podcast today. If you've enjoyed it, do subscribe, and please recommend us to friends and colleagues and anyone else who you think would be interested in what's happening in the cement and concrete industry around the world. WCA is a not-for-profit company. Please visit our website to see the services that we offer.
Clinker Factor, the cement industry podcast.